This is refracted angle, and this is incident angle, and this is point of incidence. Now this is refracted angle. When you extend this incident angle and until it meets at point O, with this extended also emergent angle backwards until it meets at point O, we will have now this whole angle to this normal dotted line, blue dotted lines. These are normal lines that meet at point C or both of the sides, point M and point N. And the angle between this normal and this extended forwards incidence rays from the sun is angle of incidence, due to these two angles are opposite angles with one transaction lines, that is normal line. Okay, and because this is R, and we know that also this is angle for incident at the edge, which is equal to angle of refraction here. How this angle becomes the same, as we know that this triangle is a equilateral triangle, as this is radius and this one is radius. If these two sides are equal, and with one side here, the base line, it says that this triangle has equal angle. This angle is equal to this angle. This is sides. Therefore, this angle is equal to this angle, and this angle remains is 180 degrees minus 2r. Therefore, at the point of incidence here, the incidence angle is equal to refracted angle r. The same things for the second equilateral triangle here, where we have a radius also, then we know this is refracted angle, which is like incidence angle that take place inside, and this is emergent angle, which is like incidence angle, which is for emergent ray. Therefore, this angle also, this is normal emergent incidence here, it's also this incidence here, because these two triangles are equal, are congruent. Therefore, the angles inside is of the same. This is R, also this is R, and this is incidence as this one, and this also is incidence, because these two triangles are congruent. As you can see, we have a radius and one base, common base, and which divides the equal semicircle here. Okay, and the angle at this point, or between these two intersecting extended dotted lines, we get the angle x and angle x, which is equal to twice angle x. Now the segment OP to the M has got 180 degrees. Now when we minus with twice x is equal to deviations angle of the emergent ray from this incident ray, extended incident rays, as it appears from the clockwise directions, while for anti-clockwise directions it is from P to this directions of extended backwards the emergency rays. This is for anti-clockwise directions. A deviation angle as from anti-clockwise directions. This is deviation angle as from clockwise directions. Okay, let us consider the triangle MCO and NCO. MCO and NCO. We use these two triangles so as we can be in a position to relate the deviations angles, the incidence angles, and the diffracted angle. Okay, now we consider these triangles and we sum the angles within the triangle, one of the triangles, and is equal to 180 degrees. Remember, this is incidence, this is 180 degrees minus twice r, and this is x, as you can see here, and the another also the same, and we have the same results here. For the line segment M or P, we know that our formula is equal to deviation, which is equal to 180 degrees minus twice x. But this twice x is, as you can see here, we substitute the x, then we just enter the inside the 2, then we multiply for 2r, negative to negative is plus 2i. Then we rearrange this expressions in such a way that we will have simplified expressions as I minus r in bracket twice just be twice it plus 180 degrees minus 2r. This type of mathematics when we follow it. This is general net deviations for clockwise directions, for the clockwise directions. Okay, for a case of anti-clockwise directions, we just take 180 degrees, we minus with this deviations net, we get the directions as in anti-clockwise there, anti-clockwise. Okay, then the for the other kind of rainbow, as you can see here, we have this kind of rainbow where the rays undergoes at least more than one total internal reflections. You can see if for this pencil mark, this 1 and this is 2 and this is 3. This is for tertiary rainbow. And also for this blue one, purple one, sorry, this is 1 and this is second purple rays, and this is for red mark 1 and second. This is just a secondary rainbow. And when we have more than 3 total internal reflections, and we can have also more than 4, 5 and other kinds of rainbows that will formed after accordingly to the total internal reflection. And this kinds of rainbow is not very clearly seen by the observer eyes. Some of them they are not even visualized by the naked eyes on the skies. They become faint and can't be detected by our eyes on this when they are formed on the sky. Okay, and we'll use this secondary rainbow just to explain how we can arrive into general formula. Just we use to derive this angle of deviations for primary, the secondary rainbow, tertiary, and the so on kinds of rainbow. Remember, inside the water droplets we have dispersions. This incident rainbow dispersed into red at outsides, least deviated, with purple as the most deviated. We choose just only the purple here, and you can use that to just get the general formula for calculating the angle of deviations. Okay, we know we have first deviation here after incidence to this refracted to point B, and we will have also a second deviation here after this refracted that extended forwards to point C, with this reflected that undergoes total internal reflections inside the edge B of this spherical water droplets. And this incident at point D here, we extended forwards to point E, and the reflected rays that from D to F forming the deviation angle.